Inference. Inference refers to making statements about the general population based on a sample. So we are inferring to the population. And we especially want to make statements about alpha and beta, less so about sigma. And the kind of statements we want to do are confidence intervals and hypothesis tests. Another thing one might be interested in might be a confidence interval for a predicted value rather than a confidence interval for alpha and beta, which represents averages. But we're not interested in that today. So it's usually confidence intervals about alpha and beta, which represent averages. We are not deriving any formulas here because two reasons. One, that was already done in Stat 231. And second is they're all special cases of multiple linear regression when we have more than one x variable. So I am just throwing the formulas up here without proof, and they will emerge as special cases later on. So the estimator of beta can be shown to be Gaussian. So beta is distributed as a Gaussian distribution with expected value beta and standard error as shown. Because the estimator of beta is Gaussian, the sampling distribution of beta has also a t-distribution. No, not also, but has a t-distribution. Right? So if the truth is Gaussian, then the sampled version of it is t. So we have that expression there. And the t-distribution requires degrees of freedom. And the degrees of freedom here is n-2, where n is the number of observations. And the -2 comes from estimating two parameters in the mean structure. So estimating alpha and beta. We also estimate sigma, but that doesn't count here. So, and there's a technical reason for that, which you may have seen in Stat 231, but we're just subtracting the parameters in the mean structure. Okay, so once we know that we have a t-distribution, then we can construct a 95% confidence interval. And this follows the usual way, beta minus a critical value times standard error of the statistic beta. And then the same thing with plus. And we do that such that the probability that the random variable t stays below c with 95% chance for a 95% confidence interval. So C is called the critical value, and you have seen that critical value for the normal distribution. You probably remember is 1.96 for the 95% confidence interval. But here we are in the t-distribution, and so we don't remember the values. For a large number of degrees of freedom, though, the t-distribution converges to the normal distribution. So if you have in the order of 30, 40, 50 degrees of freedom, then more or less you can assume C is going to be in the neighborhood of 1.96 or slightly larger. So analogously, same thing, you can also construct a 95% confidence interval for alpha. Exactly same way of construction. Alpha minus critical value times standard error of alpha and then plus. Exact same way of constructing these things. Here's some regression output, and it follows a question for you. This is from the housing data, where I'm estimating house price based on floor space. And so I have an estimate here for beta. And I have an estimated standard error. I also get the t-value and I get the p-value, so I find out it's significant. But the question here is, let's try to compute the lower confidence interval limit for beta from the output. And we're going to assume that the data are large enough for the d-distribution to have converged to a normal distribution, so that you can use that 1.96 for C. That is actually true here. The output doesn't show it, but there are far more than 30 degrees of freedom. Or am I missing something here? No, I don't see the number of degrees of freedom in this output. This is our output here. So there are five choices, and please go ahead and compute the answer. This ends this segment.